Hello, my name is Jim Cullafello, and I'm the Vice Dean of Academic and Student Affairs at the Ira A. Fulton Schools of Engineering at Arizona State University. It's my pleasure to welcome you to our National Academy of Engineering Grand Challenges for Engineering Speaker Series, hosted by ASU and sponsored by the Kern Entrepreneurial Engineering Network. This engaging speaker series will focus on the 14 grand challenges for engineering in the 21st century. Esteemed speakers from across the nation will be sharing their expertise on these grand challenges and answering your questions. We are proud to be a part of the NAE Grand Challenge Scholars Program, preparing graduates to address these challenges. It's my pleasure now to introduce Dr. Ramakrishna, the Director of the National Academy of Engineering Grand Challenge Scholars Program Network, to share his welcome.
Hello, my name is Ramakrishna and I am the Director of the National Academy of Engineering's Grand Challenges Scholars Program Network. The NAE Grand Challenges for Engineering, identified in 2008 by a committee of the National Academy of Engineering, are 14 critical global challenges for engineering in the 21st century, united by the mission of continuing life on the planet and making the world more sustainable, more healthy, more secure, and more joyful. The Grand Challenges Scholars Program, inspired by the NAE Grand Challenges, reflect the rapidly evolving nature of engineering education. The goal of the program is to prepare engineers who not only have the necessary technical skills, but also the cross-disciplinary knowledge, entrepreneurial spirit, the global multicultural perspective, and a sense of societal mission needed to meet the global grand challenges facing humankind in the 21st century. As of November 2018, 65 institutions across the US and around the world have implemented this innovative educational program, and nearly 100 are getting ready to join the consortium of GCSP schools. We at the National Academy of Engineering are thrilled that Arizona State University has taken the initiative to organize this series of presentations that will highlight each of the 14 NAE Grand Challenges and provide this valuable resource not only to its own students and faculty, but to students and faculty from around the world. On behalf of NAE, I'd like to thank ASU and the Kern Foundation for making the presentation series possible. I'm eagerly looking forward to following how this series impacts and inspires the next generation to create solutions to our society's most daunting problems. Our best wishes for a successful series, and thank you very much.
My name is Amy Trowbridge, and I am the Director of the Grand Challenge Scholars Program here at Arizona State University. I'm going to be the moderator for this first kickoff event of our NAE Grand Challenges Speaker Series. Tonight, you'll be hearing from Dr. Kavazanjian talk about the Grand Challenge of restoring and improving urban infrastructure, which relates to the Grand Challenge theme of sustainability. Following his talk will be an opportunity for the audience members, both here live in person and live online, to submit questions for him to answer. And I will be, as moderator, reading those questions and delivering them to the speaker for you. So now I'm going to go ahead and introduce our speaker. So I'm very excited to welcome and introduce Dr. Edward Kavazanjian. Dr. Kavazanjian is a Regents Professor and the Ira A. Fulton's Professor of Geotechnical Engineering. He joined the faculty at ASU in August 2004 after 20 years as a practicing civil engineer. Dr. Kavazanjian has Bachelor's and Master's of Science degrees in civil engineering from M.I.T. and a Ph.D. in Geotechnical Engineering from the University of California, Berkeley. In 2013, he was elected to the National Academy of Engineering for Geotechnical Engineering for Municipal Solid Waste Management, Earthquake Hazard Mitigation, and Safety of Transportation Facilities. In August 2015, he became director of the Center for Bio-mediated and Bio-inspired Geotechnics at ASU, a National Science Foundation-funded engineering research center dedicated to the emerging subdiscipline of Bio-geotechnical engineering. Dr. Kavazanjian is an accomplished faculty who has been referred to as a visionary in geotechnical engineering, and we are honored to have him here with us today. Without further ado, please welcome Dr. Edward Kavazanjian.
Well, thank you, Amy, and good evening, everybody. I'm very honored to be the first speaker in this series, and frankly, a little bit nervous, but let's see how it goes. So as Dr. Ramakrishnan mentioned, in 2008, a select committee of the National Academy of Engineering identified 14 grand challenges for engineering in the 21st century. And so you can see the 14 grand challenges on the slide here. As a civil engineer, my subdiscipline is geotechnical engineering, I'll talk more about that later. The one that resonates with me the most is restoring and improving urban infrastructure. But it's important to recognize that these grand challenges are not mutually exclusive. So as a civil engineer who works on infrastructure, for instance, providing access to clean water is certainly an important part of what we do in civil engineering: water distribution systems, water purification systems, environmental protection systems for our water supply. Developing carbon sequestration methods is something that's going to require significant, or that has significant challenges in civil engineering and geotechnical engineering. Making solar energy affordable, the distribution system and setting up the solar networks is related to civil engineering and infrastructure. And even some of these other tasks, manage the nitrogen cycle. The center that I manage, we're working on removing nitrogen from stormwater that's responsible for some of the eutrophication of freshwater bodies. Providing energy from fusion, someone has to build the infrastructure and the facilities that support the fusion reactors. Engineering the tools for scientific discovery. Back when I was a consulting engineer, I worked on the ill-fated superconducting supercollider that was proposed for Texas. And recently I've been involved in the long baseline neutrino experiment, where they want to shoot a beam of neutrinos from Illinois to the bottom of a deep mine in South Dakota. They have to build a 1,000-foot long tunnel for the beam, and that tunnel dives beneath the water table, and it has to be waterproofed. So this is part of the infrastructure of a tool for scientific discovery, and even preventing nuclear terror has some aspects related to infrastructure. So what is infrastructure? So when we talk about urban infrastructure or civil infrastructure, these are the fundamental systems that a community relies upon to support the society that we live in, the civilization that we live in. And what does it include? Well, we have transportation systems, water supply systems, power systems, housing, industry, business facilities. Basically, all of the systems that support our everyday life. Why is infrastructure important? Well, infrastructure is directly related to both the quality of our life and economic prosperity. We provide shelter, it provides mobility for us. I already mentioned water supply, power supply, sanitation, food supply, manufacturing. All of these things rely on the urban infrastructure. The problem is that the infrastructure we have in the United States that's supported our very high standard of living is not in very good shape. And so the American Society of Civil Engineers issues periodically an infrastructure report card for the United States, where they grade the various systems that comprise our civil infrastructure. And right now, the grade that the infrastructure gets is D+. And you don't have to be an A+ student to recognize that a D+ is not a very good grade. ASC estimates that by 2020, if we're going to bring the infrastructure up to like a B grade, we need $3.6 trillion in investment in the infrastructure. And the cost of not bringing our infrastructure up to grade by 2025 is $3.9 trillion on the gross national product, $7 trillion in lost business sales, 2.5 million jobs lost, and $3,400 per year per family in costs due to inadequate infrastructure. A good example of how infrastructure can spur prosperity is the interstate highway system. The interstate highway system started under President Eisenhower in the 1950s, was really the engine for economic growth in the United States in the second half of the 20th century. Unfortunately, many of the roads that were built in the 1950s and 1960s and 1970s are starting to decay because of deferred maintenance and lack of attention to upkeep and renewal. So we not only need to improve the infrastructure, but we need to restore it. And to me, that's important that the way it was phrased in the Grand Challenge was restore and improve infrastructure. I already mentioned the grade of D+ that we get for our infrastructure. Due to lack of investment in maintenance and renewal, you know, when the budget crunch comes, what do our public works agencies do? Well, they defer maintenance. It's one of the easiest ways to make your budget balanced. And so we have a gradual decay in functionality and capacity, and it's a gradual decay that is occasionally punctuated by some very extreme events. So for instance, the picture in the lower left there is the I-35 bridge over the Mississippi River in Minneapolis that collapsed dramatically in 2007, killing a number of people and putting a vital artery out of service for a sustained period of time. So our existing infrastructure is stressed. It's stressed because it's old. It's stressed because we have growing population that relies upon this infrastructure and puts a greater demand on the systems. We're seeing greater concentration in urban areas, so that further stresses the system, and often in coastal areas that are going to be very susceptible to climate change and sea level rise. And so ASC estimates that on an annual basis, there are 6.9 billion hours of delayed in traffic, 42 hours per driver just due to inadequate infrastructure. Water quality is something that we often take for granted. If you've never traveled outside of the United States, well, once you travel outside of the United States, you realize how spoiled you are by the fact that just about any place in the United States, you can take a glass of water, you can walk up to the tap, open it up, and drink that water and not worry about your health. In most of the world, that's not the case. But we take it for granted. It's essential to health and well-being. We only notice it when it fails. And so the Love Canal was an example of poisoned groundwater resources. A civil action, Erin Brockovich, Flint, Michigan, it fails and we make a movie about it, right? But we don't necessarily take the actions that are necessary to prevent it from happening again. So if you look at how infrastructure has developed, prior to, say, 1950, civil engineers who worked on infrastructure, their objective often was to build heroic structures, from the pyramids to the interstate highway system, Hoover Dam, Empire State Building. We wanted to build the biggest, the best of everything. 1950 to 1970, civil engineers started paying attention to something we call life cycle cost assessment. When we looked at options, for instance, when we built the interstate highway system, and we wanted to decide whether to use concrete or asphalt for the pavement, well, the concrete costs more, but the long-term upkeep is cheaper and it lasts longer, and so how do we balance those? So we started doing life cycle cost assessments to select between alternatives. From 1970 to 2000, sparked in part by the Love Canal and other environmental disasters, really, we started doing environmental impact statements and looking not only at the cost, but at the environmental impacts of our projects and trying to develop mitigation measures if we had unavoidable environmental impacts. In the dawn of the 21st century, sustainability and resilience became important. Social equity became a factor in our decisions, and hazard mitigation to provide more resilient infrastructure. And these days, the coming challenge is adaptation to climate change. Or mitigating climate change through carbon sequestration and adaptation to the inevitable impacts that are going to occur, even if we're successful in reducing our carbon emissions. So I wanted to mention, so the picture in the middle here, this is the Verrazano Narrows Bridge. And at the time it was being built, it was the longest suspension bridge in the world. And it's why I became a civil engineer. My father was in the Veterans Hospital in Fort Hamilton at the foot of the bridge, and I think that's the building there, that's the Veterans Hospital. Children weren't allowed in the hospital, so when Mom went to visit my father, I stayed in the car with my grandmother, and I got to watch him building this monumental structure. And that is what gave me the desire, I wanted to build things like that. Now I get kind of down in the dirt rather than up in the air, but nonetheless, it was an important fact. And then the Love Canal certainly was a watershed moment in terms of paying attention to the environmental impacts of what we do. So these days, it's all about sustainability. And we look at sustainability as a three-legged stool. We look at the economic effects, life cycle cost assessment. We look at the environmental effect. We'll do a life cycle environmental assessment. And then we look at social equity issues that are associated with what we're doing. I was at an ASE function recently, and somebody was challenged to give a short and succinct definition of sustainability. And I thought it was very eloquent. He put it in 4 words, that sustainability means enough for everyone forever. So we not only want to provide for our current needs, but we don't want to compromise the ability of future generations to meet their needs. Our focus these days is on urban areas. They occupy a very small percentage of the Earth's surface, but they disproportionately exhaust resources and generate pollution compared to the amount of area they occupy. So with sustainability, we're paying more attention to environmental and energy use considerations. And as I mentioned, we also try and consider social equity when making our decisions and weighing the trade-offs. All right, so how do civil engineers contribute to sustainability? Well, one is through these processes of life cycle cost assessment and life cycle environmental assessment, not just what the immediate impact is, but what the long-term impact is. But we can also contribute through technological development, developing new means and methods for construction that are less energy intensive, developing new materials or using new materials that have a smaller carbon footprint than our existing materials. We can contribute to maintenance, rehabilitation, and end-of-life treatment of existing infrastructure. We can contribute to environmental protection and in environmentally degraded areas through ecological restoration. An important function is being more efficient with both our design and construction processes, mitigation of natural hazards, and adaptation to climate change. So efficiency in design and construction is something that I think often gets overlooked in terms of its contributions to sustainability. When I was interim chair of the civil engineering department here, and I was talking to somebody about our program on asphalt technology, I was told, well, asphalt's not a sustainable technology. We're using hydrocarbons and it has all these environmental impacts. But the fact is, every day enough asphalt is placed in the United States to pave a 4-inch thick lane of traffic from Los Angeles to New York. That's every working day. If we could reduce that to 3.5 inches, if we can extend the life of that pavement from 20 years to 30 years, we'll make a substantial contribution to sustainability. So by being more efficient with our design processes and our construction processes, and NAE recognized that. You know, this is a quote from the NAE website, that good design and advanced materials can improve transportation, energy, water, and waste systems, and also create more sustainable urban environments. Resilience and hazard mitigation has taken on a greater, occupied more of our attention recently, in part due to recent disasters that highlight the fragility of our infrastructure systems. As our urban areas get more crowded, extreme events tend to have greater impacts. Katrina, back in, what was that, 2007, was at that time referred to as perhaps the greatest civil engineering failure in US history, overtopping of the dikes and flooding of New Orleans. But you know, since then we've had more than our share of similar incidents. Hurricane Sandy, I grew up on the South Shore of Long Island. My mom's house had 6 feet of water in it in Hurricane Sandy. Recently, Hurricane Michael in Florida, Hurricane Maria in Puerto Rico, Hurricane Harvey in Houston, and then earthquakes, Christchurch and Tohoku. Christchurch, city of Christchurch, modern construction, a moderate earthquake, 15,000 single-family homes were damaged beyond repair by the earthquake, and the entire central business district was devastated, and 7 years later is still a ghost town. Adaptation to climate change is probably the newest challenge that we have to face. Human activities are having a profound impact on the environment. Some of my colleagues like to use the phrase, the Anthropocene. Welcome to the Anthropocene, the age where human activities are influencing climate and geosystems. The impacts associated with or exacerbated by human activities include rising sea levels, changing climate regimes, more extreme weather, and flooding in urban areas. And that's an interesting one. This is a picture from Houston. You know, the more we pave urban areas, the faster the stormwater accumulates and the greater flood hazard we have in urban areas. My hydrologist friends talk about the time of concentration. The time of concentration goes down, so we have a greater surge of water that leads to greater flooding. And it's pretty much an inevitable impact of urban development. So that's a general overview. I thought I should say a few words about what I do. I'm a geotechnical engineer. I deal with the mechanics of soils, design of foundations and earth structures. And unlike a lot of people who like to look up, as David Macaulay noted in his book Underground, things are looking down for geotechnical engineers, and that's a good sign. We like to look down. My mother would tell you that I did dirt and garbage. I work on soils and I work on landfills, and she says I was made for that because ever since I could walk, I was bringing dirt and garbage in the house. Waste containment systems. You know, when I was a consulting engineer and we were working for the city of Los Angeles on an expansion of their landfill, we'd go to a hearing and there were always people who stand up and say, we should close all the landfills. If we close all the landfills, people will find other things to do with their garbage. Well, I was in the Philippines right after the municipal landfill in Manila failed. And yeah, people found the landfill closed, people found other things to do with their garbage. They dumped them in every vacant lot. They dumped them on every median. There were big plastic bags of garbage all over the city. If we find other things to do with our garbage, then the landfills will close. That's the way to look at the problem, in my opinion, not let's close landfills and then force people to find other things to do with their garbage. Lately, I've been involved in this emerging discipline called Bio-geotechnical Engineering, where we're looking to nature to provide us with sustainable solutions to infrastructure development. So if we look around us in the natural world, we find that nature has developed many durable and efficient geotechnical systems. And so we have some pictures here. These are the White Cliffs of Dover, carbonate sediments that are very durable, they're very resistant to erosion. If it was an earthquake-prone area, it would be very resistant to earthquakes. Here's a mangrove tree. Tree root systems are much better at resisting lateral loads, wind loads and earthquake loads, than the foundations that we build today, the piles we drive in the ground or the footings we put on the ground. Ants are marvelous tunnelers. Ants tunnel with 2 orders of magnitude more efficiency than we do. When you look at the amount of energy they take to move dirt and create a tunnel, it's 2 orders of magnitude more efficient than what we spent to tunnel. We'll never get to that level of efficiency, but maybe we can learn from them how to tunnel more efficiently. Root systems, the way a root penetrates into the ground, again, is much more efficient. We often put probes in the ground for geotechnical exploration, but the penetration, the way roots penetrate is 10 times more efficient than these blunt probes that we push in the ground. So how can I design a probe that penetrates into the ground like a root and reduce the amount of energy I need to push it into the ground or be able to go deeper with my current systems? And then this guy in the middle here, I think that's Bill Murray's friend from Caddyshack. And he's a really excellent tunneler. He does a great job of tunneling in a relatively non-disruptive manner. If it's too shallow, you do see the trails at the surface. So we have this engineering research center funded by the National Science Foundation. We're in our 4th year of operation, called the Center for Bio-mediated and Bio-inspired Geotechnics. What does that mean? Well, a bio-mediated process is a process that's controlled by biological activity. And for us, as geotechnical engineers, we're typically talking about microbial activity. So we can stimulate microbes to turn sand into sandstone, to precipitate minerals that cement the sand together. And so the picture here in the middle, whoops, get it back, is an example. We take loose sand like this, we treat it with a microbe and some substrates, and we cement it into solid ground. And we can use that to mitigate earthquake hazards. We can use that to make it easier to tunnel through the ground. We can use that to make it provide better support for our buildings. We also look at bio-inspired processes where perhaps we don't use the biological process itself, but we mimic it. So this is an artist's conception, certainly, of how we could use tree roots to provide better foundations for wind turbines. Most wind turbine foundations now are big hunks of concrete that work by gravity to hold the turbine down against the high lateral loads due to winds. They're not very efficient systems, and that there are certainly more efficient ways to resist those lateral loads, and we can take our cue from nature on how to develop those systems. So this is a rendition by one of my colleagues at UC Davis, which is a member of our center, on what the biogeotechnical future might look like. We certainly can't expect that every problem in infrastructure development can be solved with a bio-mediated or bio-inspired solution, but there are a host of problems that we can address by taking our cue from nature on how to address those problems in a sustainable manner to create resilient infrastructures. And so, with that brief presentation, I guess I turn it back over to Amy.
Kavazanjian. That was a great overview of many challenges in sustainable infrastructure that we face today, and they all present great opportunities for engineers like you all in the audience to develop solutions to create value for society. I hope that all of you in the audience have learned something new about the grand challenges and are inspired to learn more and perhaps take action on some of those challenges in the future. For the remainder of the time, we'll give you, the audience, the opportunity to actually ask any questions that you want to of Dr. Kavazanjian. If you'd like to ask Dr. Kavazanjian a question, please submit them, start submitting them now or at any time. So if you're joining us live in the audience here at ASU, please submit your questions via text messaging to the number that was provided on the program. So make sure you have that program out and use that number to text questions to now. If you're watching remotely via live stream, please go ahead and add your questions in the comments directly on the YouTube channel, and we will be fielding those questions as well. So let's go ahead and take a seat, and I'll start off with a few questions of my own while we're waiting for those questions to come in. All right. So first, let's talk a little bit more about the last topic, biogeotechnical engineering. I think when many of us are thinking of civil engineering, we're picturing buildings, bridges, roads, things like that. But we probably don't think of biology at all when we're thinking of those things. So how did you first make that connection between biology and geotechnical engineering and get involved in this interesting new field of biogeotechnical engineering?
So I think it's an interesting story. I'm glad you asked that question. So in 2003, 2004, I was on a National Academy of Engineering committee that was charged with looking at opportunities for innovation and research in geotechnical engineering in the 21st century. At that time, the conventional wisdom was everything in the 21st century was going to be nano, bio, or cyber. So the committee sat around and scratched our head on how we could contribute to geotechnical engineering through one of those areas, nano, bio, and cyber. And we had a microbiologist on the committee who wrote a passage for our introduction to the report that said, imagine if we could build the tunnel lining first and then tunnel through it and leave the lining in place behind us. Imagine how efficient that would be. And that really caught my imagination. So I sat down with Dave and I said, you know, what are you talking about? How can we do this? Well, he made a convert of me. And so I went home. Actually, that was just when I was starting at ASU. Okay. So the first research proposal I wrote at ASU was to the National Science Foundation and was to try and look at the prospects with developing these kinds of technology.
Wow, very interesting. So inspired by other colleagues about fields that you didn't know a whole lot about.
Correct.
Awesome. Cool.
In fact, I became a civil engineer because I didn't want to take biology or chemistry. You know?
Some of our audience can probably relate to that. I know myself, I actually hated biology in high school, but then ended up doing biomedical engineering. So I'm not sure how that happened, but interesting turn of events there. So during your talk, you mentioned several reasons why infrastructure is important. As well as examples of challenges and possible solutions. So as an expert in this field, what do you feel is the most important challenge or the challenge that's most pressing that we really need to face in sustainable infrastructure today?
I think certainly the most important challenge is perhaps not the technical one. It's developing the will to provide the resources we need to improve and restore our infrastructure. Okay. You know, it's not going to be cheap. Yeah. The real question is, where is the money going to come from? And do we have the will as a community to finance what
Okay.
needs to be done.
So not a technical issue at all, really.
I don't think
But they're
so.
more of a
Yeah.
societal public perception as well as policy type issue.
Yes.
Cool. So it looks like we've already got some audience questions. So I'm going to go ahead and jump to some audience questions here. So first one, if you could create your own smart city, what key features would it have?
So I think one of the features, I think we need to rework our transportation systems. Everybody, living out in the suburb and getting in a car and driving into the city every day, and then, getting back in the car and driving home and getting stuck in traffic jams. I mean, that's really not a very efficient way to organize a system that a city really is. So I think kind of a planned community where we can minimize the amount of time and effort we spend moving from one place to another and doing our daily tasks. I probably would start there.
Okay.
And I'd put a lot underground.
A lot underground, all right. So instead of closing landfills and expansion, what do you think personally would be an efficient way to make the garbage system more sustainable?
Well, I think, I have colleagues in the industry, and they really are concerned about that. So for instance, recycling, the 3 R's, reuse, reduce, recycle. So let's reduce the amount of garbage we're sending to landfills. Let's reuse whatever we can, and what we can't reuse, let's recycle. And we have some pretty good systems, but it sometimes takes cooperation. When you talk about recycling, there are 2 ways to do recycling. One is the single container. You put everything in a container and you put it out on the curb and someone comes takes it away. The other is where the homeowner separates the recyclables into paper, glass, puts it out in separate containers. That second system is a much more efficient system in terms of recycling. But in terms of the volume you get, people are just too lazy to do that. So we need to educate people to do the right thing, even if it takes a little bit more effort.
Back to society and people again here. Absolutely. All right, so we'll go ahead. We have a question from our online audience. So how do differing climates affect how geotechnical solutions come about? And what are some solutions that are Arizona specific that you've worked on?
So in Arizona, the challenge is we have an arid climate. It's very dry. A big environmental problem in Arizona is fugitive dust. And I love that term, fugitive dust. I think the little dust particles running from the law, and we're going to capture them and put them back in place. But dust is a big problem in Arizona. It has health impacts. It's associated with an increase in valley fever. It's a problem that's unique to arid areas. And one of the biogeotechnologies we work on is dust suppression, is providing a calcium carbonate crust using a bio-inspired method to stabilize the soil from blowing dust. In other areas, if we're in a northern climate, the frost heave could be a big geotechnical problem. If we're in a really wet climate, then, surface water, erosion. Well, even in Arizona, when it rains, it pours.
Yeah.
So we do have problems with scour of bridge foundations and erosion.
All right, so with this next question, we're going to shift to water a little bit here and a specific water crisis that we've heard about in the U.S. So do you know what is being done to fix Flint's water crisis?
I don't.
Okay, that's an easy answer.
I wish
Look
I
at
did.
that.
I don't.
Any thoughts on it? No. All right. I thought I'd ask it. It was worth asking.
Yeah.
Maybe you would know and have some insights for us. So let's see. All right, so recently there was a proposition for Arizona voters that didn't pass. It was a proposition for electric utilities in Arizona to acquire a certain percentage of electricity from renewable resources each year. How sustainable do you think that proposition would have been if it were passed, given economical, environmental, and social factors? That's a good question.
It is, and it gets to the weighing those different factors. So I think from an environmental perspective, it was a good idea. The more renewable energy we have, the better off we're going to be. But there's a cost associated with that. And frankly, the voters decided that they didn't want to pay the incremental cost that was associated with that higher level of sustainable development. I could tell you which way I voted, but I won't.
All right, that's a good question.
But it's a good lesson because it's a common trade-off, and I find, for instance, the European communities are much more willing to pay a little bit more for a more sustainable solution than we are in the United States.
All All right. One major problem we are facing is excess carbon in our atmosphere. How can we use biogeotechnical engineering to alleviate this problem?
So we can contribute to carbon sequestration. The carbon precipitation technologies that we use to strengthen soil also take carbon out of the environment and stabilize it. But I think the real answers are, one, reducing carbon emissions. And actually, we can contribute to that, too. You know, one of the major sources of carbon emissions is concrete, Portland cement concrete. 5 to 7% of the world's greenhouse gas emissions are due to the manufacture of concrete. Our precipitation technologies would replace concrete as a binder for granular materials. So that would reduce the amount of greenhouse gas generation. The technologies to take carbon out of the air and sequester it in the ground, they tend to be abiotic. But they're still nature-inspired. They're maybe not bio-inspired, but they're nature-inspired.
Okay. So you mentioned an alternative to concrete? Awesome. Okay.
That's our geoalchemy. We turn sand into sandstone.
Okay, very interesting. Let's see what next question we want to have here. All right. So what are your thoughts on the potential for green infrastructure for contributing to sustainable urban areas? Trees can reduce energy demand and waste streams and improve quality of life.
Well, I think, yeah, certainly improving the quality of life is a big part of it. You know, I'm not an expert on it, but you read conflicting reports about, you know, the trees would emit more carbon dioxide than they take out of the atmosphere. I don't know. I suspect that in general they're beneficial. But there are a lot of other benefits to green infrastructure too. So for instance, groundwater infiltration, preventing that big surge of stormwater that floods the streets and floods our communities when we get a heavy rain. So it's certainly a good idea, but it's tough to do sometimes in existing communities. So if you're planning a new community, I think you can plan for that. But if you have an existing urban environment, whether it's Phoenix or Los Angeles or New York City, it's hard to find, you know, the green space. The real estate is very valuable, and there's a reluctance perhaps to dedicate it to green space. But I think a lot of, you know, the regulations now for new housing developments certainly mandate a certain amount of green space be provided.
All right, let's see. A little bit different here. Can you give an example of an innovation in civil engineering that has substantially addressed the grand challenge of restoring urban infrastructure? And hopefully something that maybe the audience will recognize. We'll see.
Boy.
I know that's a hard one.
It is. It is. I like to think that some of our biogeotechnologies are going there. I'd have to really think about that one. That's a hard question.
That is a hard one. Let's see. All right, so during your talk, you mentioned many different ways in which civil engineers can contribute to sustainability infrastructure. But obviously our audience is more than just civil engineers. It's lots of different types of engineers and also majors outside of engineering potentially. And so what about those other engineers? Are there ways that other engineers or even disciplines outside engineering can contribute to sustainable infrastructure and the challenges you mentioned today?
Well, absolutely. I mean, you know, it's not, the urban infrastructure isn't just the civil systems, but it's you know, electrical systems, mechanical systems, you know, big data, geographic information systems, earth science, climate science. I mean, just about every discipline you could think of, some way, you know, factors into infrastructure.
Okay.
And, you know, certainly, so for instance, providing a more climate efficient, a more energy efficient building. You know, what does that take? That takes information systems, it takes electrical systems, it takes mechanical systems, it takes sensors. You know, it's a network of systems that all contribute to the infrastructure.
Okay. Let's see. Oh, an interesting one that just popped up. So what is your input on the autonomous garbage patch cleanup system that was launched in September?
So I only know.
I haven't even heard of that, honestly. Go ahead.
I only know what I read in the paper, but certainly, you know, plastics in the environment are a big problem, and you know, there are the large, you know, patches of plastics out there in the ocean. But I think even as important, maybe even more important, I think on an environmental level, these plastics are starting to degrade, and some of the chemicals are starting to get into the sediment and then into the food chain. So we really do need to reduce our reliance on plastics.
Absolutely, absolutely.
And hopefully eventually clean up the mess that we've already made.
Yeah, Yeah, definitely. Let's see. We have one related to kind of new technologies. So they're asking about, so what are your views on emerging research areas such as concrete 3D printing? And how big a role would these 3D printing processes play in addressing these grand challenges, or this grand challenge?
So I don't know about 3D printing of concrete specifically. I think 3D printing has a lot to offer. I don't know on a large scale, like a bridge, how realistic it is that they're going to contribute. There are other aspects of concrete technology, though, that are very important. That go to this idea of efficiency in design, higher strength concrete, so you need less, more durable concrete, so it lasts longer.
Yeah.
So certainly, concrete may seem pretty mundane, but there's a lot of high technology and material science that goes into making better concrete.
Interesting. So we had a follow-up question on one of your previous responses talking about the alternative to concrete, and they're asking, could we hear more about that?
Well, I'm looking at my graduate student out here in the audience, we have basically what we're doing, soil is a porous material. And so in a granular soil, like a sand or a clay, the pore spaces are pretty big. They're often filled with water. And of course, they're a host of millions of microbes. And some of these microbes catalyze the precipitation of minerals from the seawater. And there are lots of examples. I mean, shellfish that draw the calcium carbonate that forms the shell in the shellfish is drawn from the seawater. You look at natural deposits of carbonate sands and carbonate cemented sands. So we have this geological process that can take thousands of years. But what we've learned how to do is how to speed it up so that it can take weeks if the conditions are right. So we stimulate microbes that are already in the ground to induce the minerals to precipitate out of the pore spaces, and in doing so, they cement the soil particles together.
Interesting. Very interesting. Let's see. So we've been talking, or when you were describing the infrastructure challenges, there was some reference specifically to challenges and examples to challenges and infrastructure report cards in the US. So do other countries face similar challenges, or how might their challenges be different, at least that you know of or that you can speculate?
I think certainly similar challenges. Okay. One of the things, I think in the US, it's a little bit of a mixed blessing. In Europe, there were 2 world wars that devastated their infrastructure, so it's a lot newer than our infrastructure. So it perhaps isn't as quite the state of disrepair. We have a lot of older cities with sewer systems that are over 100 years old, with water distribution systems that are over 100 years old. In Europe and Japan, there's been a lot of renewals since 1945 in those systems. But certainly they'll face the same. Still their infrastructure is aging, and so they face a lot of the same problems for renewal.
Okay. So several questions I think came up, and students and audience members seem to be intrigued by some of the societal aspects that came up and the social impact side. And so there's a lot of questions here now asking about what can we do to kind of change people's minds and people's behaviors about this. So let's see, how should we change the general perspective on sustainability? Is the key to make changes in the education system?
So, that's certainly the toughest issue. People issues are always tougher to handle than technology issues.
Absolutely.
I think, So certainly education's part of it, but not just education. You need to speak up. You need to try and educate, your fellow citizens, and not accept these things without, letting your opinion be known, and trying to educate. Not just formal education in school, but try and educate the community that you live in about the importance of these considerations.
And how do we do that? So how do we get people to realize how crucial it is to change our ways and become more sustainable because some people are resistant to changing their ways? Get
involved, go to meetings, go to public hearings, participate in the discourse. Don't just stay in your comfortable little space and not get engaged. So, but you have to partake in the discussions, in the discourse.
Absolutely. So there's one question here that was about traffic, actually. So a totally different side, but something you mentioned in your talk today. So in the presentation, you mentioned that 42 hours per driver is wasted every year in traffic. What causes traffic, and what's the solution? Another big open question.
What causes traffic? I mean, I guess the traffic engineers would say the system doesn't have enough capacity.
Yes.
Well, it's either the system doesn't have enough capacity or there's too much demand on the system. So if we want to get rid of traffic, we either need to increase capacity or reduce demand. From the engineering perspective, that sounds simple. It's straightforward, but perhaps not so simple. How do you reduce demand?
Absolutely, cool. Yeah, that one I think was one of those where the answer depends on who you're asking. It sounded like.
Well, mass transit. I have a friend who's a mass transit planner who says that people look at mass transit as something that everyone else will use so they can still drive their cars and not get stuck in traffic.
Yes. All right. Let's see.
And we will have a streetcar in Tempe soon, right?
Yes. There's all kinds of innovations in cities all over the states and the world, of course, trying different solutions. Interesting. All right. So what are your goals for the topic area of sustainability that you wish to achieve?
Well, I think we want to continue developing and commercializing these solutions that we're developing for sustainable and resilient infrastructure. Personally, I do a lot of work in earthquake engineering, and one of the hazards that we're trying to address with our carbonate precipitation, our geoalchemy, is earthquake-induced liquefaction, which is, there are literally trillions of dollars of infrastructure at risk from this phenomena. I mentioned in the presentation 2011 Christchurch, a moderate earthquake, magnitude 6.3, $30 billion in damage from a single earthquake. Magnitude 6.3 was the Long Beach earthquake in 1933, except it wasn't in Long Beach, it was in Newport Beach. And in Newport Beach, California, the cheapest house is probably $1.2 million. So, put that earthquake back in Newport Beach, and that one earthquake, you're looking at, billions, tens of billions of dollars of damage. And direct damage, not the indirect damage that's due to the disruption of commerce and the disruption of people's lives. So, we're really focused right now on developing this technology for mitigating this particular geologic hazard.
Interesting. Let's see. How will 5G impact city planning?
I have no idea.
Okay, good. Some of these are random questions. Just thought we'd throw them out here. Let's find another one that's. Okay, so this one relates to highways, which we were just talking about. So is it possible for a national interstate highway to exist, I think, through using tunnels completely?
Well, it's certainly possible, but the expense would probably be prohibitive. I was in Chicago recently with one of my friends, and I guess Elon Musk has a contract to build a tunnel from O'Hare Airport into downtown Chicago. And if you've ever made that drive, it doesn't matter what time of day it is, it's a miserable drive. And then, he also has these plans to build this underground superhighway from New York to Washington, D.C. And we all laugh because it seems like he thinks he can magically reduce the cost of tunneling by an order of magnitude. And maybe he can, maybe he knows something we don't know, but tunneling is very expensive.
Yeah.
And again, it comes down to, so but now tunnels last a long time. They could last 100 years. So if you're willing to amortize that cost over 100 years, which we don't do in any of our economic analyses, maybe it does make sense. But so again, it's one of those trade-offs. I remember in Washington, D.C. when they were planning an extension in the metro, and the question was, should we put it below ground or above ground? And if they put it below ground, they could only build so much because they only had so much money. If they put it above ground, the system could extend a much greater distance, and there were funds left over for other infrastructure improvements. So there are always these trade-offs that you have to make. But underground tunneling is expensive.
All right, so we're getting near the end here, so we'll close up with a question here. So we've been talking a lot about important societal challenges and technical work today. But to sum it up, let's talk about what brings you here into engineering. So what excites you most about engineering?
I like to build things. As I said when I showed the bridge there, that's what spurred me to become an engineer. But when I drive past a bridge where I worked on a design or on a project that I was involved in, I take great pride in having been involved in that. So,
Great.
I like to build things.
All right, thank you. So that's all the time we have for tonight's event. Thank you, audience, for all of the great questions. Some that were stumping our speaker, but some really good ones as well. It's always difficult to see what questions can be answered. So please watch our website for future events in this NAE Grand Challenges speaker series. We will be having several over the next 2 years. So audience, please join me again in thanking Dr. Kavazanjian again for a great inspiring talk this evening.